Hello and welcome to SPH3U. Today we're going to talk about distance and speed. To complete this lecture, please prepare your calculator and make sure that you've got your graphing distance and speed handout ready to work through things as we go. Okay, let's start with a problem. For an object traveling at constant speed, as the time increases, how does the distance traveled increase? Does it increase linearly, at an increasing rate, or at a decreasing rate? Well, the answer, as we saw yesterday, is that we see a linear increase in distance traveled. So for each time increment, an equivalent amount of distance is covered. Today we're going to investigate those phenomena further. So if we take our learning goals from the SPH3U curriculum, we're going to create and analyze distance time graphs and speed time graphs and see what the implications of those are. Essentially, we're going to look at slopes and areas to determine various parameters of the object as it travels. Okay, so let's look at practice question number 1. Leah jogs at a constant speed 3 meters per second for a minute. Calculate her distance traveled after 0 seconds, 10 seconds, 20 seconds, etc. Okay, pause the movie, please, and work through this table. Okay, welcome back. So, we can see that for each time increment of 10 seconds, she travels 30 meters. And so after 60 seconds or 1 minute, she's traveled 180 meters. And that's straight out of our work from yesterday with distance equals average velocity times delta t. Now, please plot the data points in your table. So put time on the horizontal axis, put distance traveled on the vertical axis, and make sure and label your axes, as always, with a graph, but in this case we're going to use this in a few seconds. Okay, pause the movie and work through that, please. Okay, so we've got our axes labeled here, and we plot our points, and we, no great surprise, see a linear plot as we covered in the question when we began. We're linear with respect to distance and time. Now, if we draw a line through the points, we can select 2 points on that line and calculate the slope. Include the units in your slope calculation, please. We're going to see why in a second. Okay, pause the movie and do that, please. Okay, so I've done mine here, and you can see based on the points I chose the 10-second point and the 50-second point. So my time elapsed is 40 seconds, and on the vertical axis you can see I chose the 150 meter point here, the 30 meter point here, subtract and get 120 meters. And then to calculate the slope, rise over run, of course, is 120 meters over 40 seconds equals 3 meters per second. Okay, so if we consider that fact for a second, that our slope is 3 meters per second, essentially what we started with, you might remember. We have a slope of 3 meters per second. What are meters per second? What do they measure? Well, they measure velocity. So we got from our units, we can see that we have extracted the speed from a distance time graph. And of course, if you remember from math class, the slope is the change in distance with respect to time, which is, of course, speed. Okay, so the slope of a distance-time graph is the speed. The steeper the slope, the higher the speed. The shallower the slope, the slower the speed. No great shock. Okay, Leah's speed's constant, right? So she's running at 3 meters per second. There's an interesting distinction here between her average and her instantaneous speed. Her instantaneous speed, her speed at any given time, is always 3 meters per second, even at 0 time point. So she was moving at 3 meters per second, even at 0 time. So now if we go to plot her speed versus time, we can do that based on taking her speed at each given time interval. So please pause the movie and do that now on your practice sheet. Okay, so we can see mine here. I've got dots at 3 meters per second all the way across, constant speed. Now if we draw the line through the points, obviously our slope is 0. In other words, the change in speed is 0 all the way along. But what we can do once we've drawn that line through is we can get the area between the line and the horizontal axis. Okay, so let's do that now. If we take the area of a rectangle, our length is 60 seconds. Our height is 3 meters per second. If we multiply 60 seconds times 3 meters per second, we get an area of 180 meters. So that's an interesting point, right? If we followed through our units, our area on a speed-time graph, the units are in meters, distance traveled. And this is our important takeaway message from this. If we have a speed-time graph, the area underneath the curve is the distance traveled. And it doesn't matter what the shape is. So it can be a convenient rectangle if that's the situation we've got. But if we have an object like this one that's changing speed as we go, well, that's fine too. The area underneath it is still the distance traveled. So we've got a useful practice problem. Number 2. Erica jogs at 3 meters per second for 30 seconds, then 4 meters per second for another 30 seconds. We need to draw the speed-time graph of her motion, and we'll see in a second that this graph will have a discontinuity at 30 seconds. Okay, so go ahead and pause the movie and please draw that out. Okay, welcome back. We've got mine here. For the first 30 seconds, we can see that she's got a constant speed of 3 meters per second, and then she, at 30 seconds, boom, she accelerates out to 4 meters per second and stays constant at that. So there's her 1 minute speed profile. Okay, so we've learned about the area under the curve gives us the distance traveled. Please use this speed-time graph, calculate the area in order to get the distance traveled at 10-second intervals. Okay, so mine, you can see it here. I've calculated a series of rectangles. They get wider as I go. And then the discontinuity here. So at this point, at 30 seconds, we've got 30 seconds times 3 meters per second equals 90 meters that she traveled at this point. Then she accelerates up, and we can add the additional increments here. So now we've got 10 seconds at 4 meters per second, 20 seconds at 4 meters per second, and 30 seconds at 4 meters per second. So her total is the total of those, you can say 6 rectangles or 2, depending on how you look at it. In this case, 2 rectangles, to get us 210 meters as her distance traveled over 60 seconds. Okay, so what if we plot a distance time graph then? Please do that now. Okay, here's mine here. I've got 2 separate segments here. If you look closely, you can see that the slope changes after the 30-second point and gets steeper. So if I draw my line in, you can see these 2 lines are not, congruent. So we have then something that isn't exactly a triangle. If we take the slope, though, of the line connecting the first and last points in the graph, that will still describe a triangle. And that slope, we can still calculate the slope of that line that doesn't connect the points but connects the first and last points. And we get 210 meters divided by 60 seconds, or 3.5 meters per second. So what's that 3.5 meters per second? Well, that's the average speed, right? So across that 1 minute, she traveled 210 meters. We can calculate her average speed very easily. Total distance traveled divided by the time interval.